Hello, you guys. We're gonna go ahead and continue our amazing journey through the Unit 0 notes. In the last video, we talked about topic 1, but today in this video, we're gonna look at topic 2, where we're gonna take a closer look at how we organize and display data that's been collected from an experiment. So in topic 2, basically what we're going to look at is we're going to look at graphs and the different types of graphs that you can use depending on what kind of data you have, and when you should use different types of graphs to display your data depending on what that data is. And so in science, I'm sure you're familiar with the fact that when we do experiments and we collect data, a lot of times you might you might not be surprised to know that we show that data using data tables, and then visually display that data oftentimes using graphs, which allows us to more easily see patterns or trends that are occurring in the data that we collected and the variables that we were testing. In AP Bio, there is a handful of graphs that you guys need to be super familiar with that do show up on the AP test, and then you'll also be having to construct certain graphs for certain questions. In the labs that we do throughout the year, you guys will be constructing graphs. And then even on the AP test, there is always a free response question where you have to actually create a graph as part of the free response question. And so the quicker you get better at this, the easier it's going to be, because we're going to be doing this a lot throughout the year. So let's start with the first type of graph. There's bar graphs. Usually students are super familiar with bar graphs. This is a graph that you would use when you have data that falls into categorical groups. So specific categories of data that you took measurements on, and you want to display that in a way that you can easily see the differences that occurred between those categorical groups. That's when you use a bar graph. So examples of different categories or categorical groups would be like sex, like male or female, grade levels. Those are different categories of individuals. Even in high school, you have freshmen and sophomores, juniors and seniors. Number of siblings. Some people have none. Some people have 1, 2, 3, or more than that. Favorite types of movies, action, adventure, romance, comedy. Those are different categorical groups. Even groupings of times, like different seasons, or sometimes you can even count months as different categories if you're trying to look at what's happening at different months or seasons of the year, things like that. Now, when you look at a bar graph, basically, first of all, it can be horizontal or vertical, meaning that you could display the categories on the X or the Y axis, and so your bars will go up and down or left to right like this. And then on the other axis, you're going to see the variable that you were measuring, or the measurements that you were taking within those groups. So that's bar graphs, pretty easy. Now histograms, students are usually a lot less familiar with these type of graphs. These look a lot like bar graphs because, go figure, they do have bars, but these technically are not bar graphs. A histogram is used to show the distribution of outcomes, or what we call the frequency of outcomes, that fall into different ranges. And in a histogram, what we're doing is we're taking a measurement of a variable, and that variable is a continuous variable, meaning that it's not categorical. So a continuous variable contains values that are not discrete or categorical, but exist in an infinite spectrum, basically. And so, for example, some example of continuous variables would be like your height. Your height can be measured, let's say, in inches. And every height exists, and every measurement of inches exists. And so you could be 60 inches tall, or 61 inches tall, or 60.235 inches tall. Like, it's a whole continuous spectrum of variables within that variable that we're measuring. And so other examples includes like your score on a test. Like, let's say we're looking at percent scores on a test. Yeah, you can get like a 90% or 95%, but really, like, every percent exists, like 94, 94.1, 94.2. It's a whole continuous range of values. That's a continuous variable. Same thing with temperature, same thing with time. height, like I already said, age, those are all continuous. And so what we do in a histogram is we're trying to take measurements that exist along a continuous range, and we're figuring out how many times the measurements we're taking fall into specific ranges that we've set up along that continuum. And that's what a distribution is, or a frequency is when you look at how many times or the number of occurrences that your data falls into these specific ranges that you've set up along your continuous variable that you're measuring. So it's kind of maybe easier to look at examples to understand what that is. Like, let's say we're looking at the results of an exam and how students did, and we want to know, like, what's the distribution? What kind of scores did students get on this test, and what scores were more common? What scores were less common? And what does this whole distribution of the class look like in terms of their performance on that test? And so performance or points on a test, again, that's continuous, like 0 to 100, and literally every infinite value in between technically exists in terms of points. And so this person, when they constructed this graph, they decided to separate that into ranges, which is what you're going to do when you construct a histogram. And they wanted it to be every 10 points to be a range. So 0 to 10, 10 to 20, 20 to 30, 30 to 40. And what they're doing is they're tracking how many students fall into each of these ranges that they've set up, so that they can look at the whole graph here and see the whole distribution of the class and where the values were most common and less common. And so here you have somewhat of a bell-shaped curve, which is pretty normal when we're looking at a histogram. A lot of people are scoring in the middle, not so much scoring really high or really low. Same thing with the heights of these trees that they're measuring. So they're going out and finding trees and taking their heights, or measuring their heights, and they're going to count how many times different trees fall into these different ranges along this continuous variable. So a height is a continuous variable, and you can see they set up these ranges of every 5 feet and how many trees fall into those different ranges. So again, we can see the whole distribution that's occurring along these measurements that we're taking on this variable. So that's what a histogram is. Now, it does visually look like a bar graph, but the big difference is the bars in a histogram are always going to be touching, because these ranges pick up from one another. So like this one ends at 10, but the next range starts at 10, and this one ends at 20, and the next one starts at 20. And so the bars on a histogram should touch. Should be touching between the bars. That's how you know you're looking at a histogram. In a bar graph, since we're looking at specific categories, you're supposed to make the bars not touch, okay? Because these have nothing to do with one another. These are different categories that we're looking at. Even down here, we're looking at different people and how many people voted for these different people, but those people, the bars between them, there's no touching. Now there could be some touching, because for this person, they're looking at different years. So sometimes you'll see bars touching in a bar graph, but you're going to see somewhere in the bar graph that there is going to be spacing between these different categories that you're looking at. Whereas in histogram, there's not going to be those gaps. So that's the difference between the two. Hopefully that kind of makes sense. Another type of graph that you're supposed to be familiar with an AP Bio is box and whisker plots. I'll start by saying that these I've almost never seen come up on test questions or on the AP test, even though the College Board says you're supposed to know this for this class, and you're supposed to know how to construct one. So I'm going to go over it as quickly as I can, and then try not to be too overwhelmed, though, because I usually don't see a lot of this come up at all in this class. But a box and whisker plot is actually kind of like a histogram in that it's showing you the distribution of data points that you collected and where all those data points fall into along a continuous range of values, just like a histogram. Now, to construct one of these charts, what it's displaying, it looks like this. There's a box, and then there's these whiskers that pop out of the box. You should have learned how to construct these actually in middle school math. I believe it's a standard, but that was a long time ago. You need to know something called the 5-number summary for your data, and that's what this is going to show you. It's going to show you 5 important numbers from your data. It's going to show you the maximum value out of all the data. What was the highest value? which is going to be over here. It's going to show you the minimum value, what was the lowest value that you collected. And then you're going to look at what's called the median, which is the middle value of all the data you collected. And then you have what's called your upper quartile and your lower quartile, or Q1 and Q3. And then the median is Q2. And so what you end up doing is you basically end up dividing your data into fourths. You have this fourth, this fourth, this fourth, and this fourth. And each of those chunks actually represent 25% of the data points. So if you look over here, we can actually use this to compare the distribution between different things. Like in this case, we're looking at customers per day at store A and store B. And so there was all these numbers collected each day. They measured how many customers came. And what they're showing you is a summary of all that data that was collected. They're showing you the minimum value, the lowest number of customers that showed up on a given day at store A and store B, the highest number of customers that showed up on any given day, the median number of customers that show up on any given day. But again, this is showing you the data chunked into fourths. And so what that means is for store A, if you're looking at that, 25% of the days, there's this many customers between this value 200 and 400, 25% of the days. And another 25% of the days, there's between 400 and 500. And another 25% of the days, there's 500 to 550. And another 25% of the days, there's 550 to 600. Which really means like half the days, there's 500 to 600 customers. So most of the time, there's customers in this that fall into this range on a given day at store A. And you can see at store B, the distribution's a little bit lower overall. It never goes quite as low. It never has quite as bad of a day as store A, or as good of a day as store A. But you can even see the median value is lower than store A. And you can see that 50% of the customers fall into between this dot and this dot, or between this dot and this dot, or between this dot and this dot, because each of these dots represent 25% of the time. And so that's basically what you're looking at in a box and whisker plot. I wouldn't worry too much about it. You do need to know how to construct one. So in here, there is instructions on how to construct a box and whisker plot and to figure out those 5 numbers so that you can plot them. Basically, what you have to do is you have to first arrange all of your numbers in a data set from smallest to largest. I'll show you an example in a second. And then the minimum value, that's your smallest value, and the maximum is your largest. So those are the 2 endpoints of your whiskers. Now the median value, this line in the very middle of the box, that's going to be the middle number when you have a total amount of numbers that's odd. And if you have an even amount of numbers, it's going to be a little bit trickier because you're going to have to take the average of the 2 middle numbers. So here's an example that I think might be easier. So if the total amount of numbers is odd, like in this case, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values. So that's odd. There's obviously a minimum and maximum, and then the median is a nice just one number. It's 11. Like if you order this from largest to smallest, there's going to be 5 on this side, 5 on this side, 11's in the middle. That's your median. Or Q2. And then Q1 and Q3, your upper and lower quartiles, that's going to be the median from the first half of the numbers. And then this is going to be the median for the second half of the numbers. Now, so that's how you figure that out. And so there's 2 numbers to the left, 2 numbers to the right, 2 numbers to the left, 2 numbers to the right, and that's how we get Q1 and Q3. Now, if the total amount of numbers is even, it becomes a little trickier. Like in this case, there's a total of, I think, 12 numbers, or 1, 2, 3, 4, 5, 6, yeah, 12 numbers. So there really isn't an even number, because right here, there's 6 numbers on the left and 6 numbers on the right, but that's between 75 and 79. So what you have to do is you have to take the average between them. So you add them together and divide by 2, which would be 77. So really the median would be 77. And then you're going to take this half, the first half of the numbers, and you're going to find the median between them to find your lower quartile, which again, you're going to end up with 2 numbers that you have to average because there's going to be no nice number in the middle. So it's going to be 59 and 68 because then you're going to have 3 and 3 on each side. So you're going to take the average between them, which would be 63.5. That's Q1, your lower quartile. And then your upper quartile, again, you're going to do the same thing on the larger half of these numbers and find the median, which again is going to be two numbers that you have to take the average of. But that's basically what you do, and then you use those numbers and you plot them over a number line, basically, like right here. Like you're going to plot the lowest number, the highest number, your median value, and then your lower quartile and your upper quartile, and then make a box, and then make your whiskers. That's how you do it. There's a couple examples in your notes that you'll practice and see if you can figure out how to construct it. Moving on from that, you now have two more types of graphs, or three more. There's scatter plots. A scatter plot is used to show the overall relationship or correlation between two variables. So this is when you're measuring two different variables that you're collecting data on, and you want to know if there's any overall relationship or correlation between those two variables. Like if one gets higher, does the other one get higher? If one gets lower, does the other one get lower? Or if one gets higher, does the other one get lower, or vice versa? And so you want to see if there's an overall trend between those two variables. And so you're going to collect all these data points and you're going to plot them all and see if there's an overall trend that you see between those variables. And so in this case, when you're doing a scatter plot, both axes, both variables that you're measuring are going to be continuous variables. So again, values that exist along an infinite range of or infinite spectrum. Like it's a whole range of values that it could be. And so, for example, this is showing the elevation at different places in Nevada, I think. I don't know what this is. Yeah, Nevada. And then the average temperature. And so they found all these places. They took their elevation, what elevation is it? And then they found their average temperature, and they made a plot, a little dot here, a data point. And they did that for all these different places in Nevada. What's the elevation? What's the average temperature? And they plot it all to see if there's an overall trend. Same thing here. They're looking at your grip strength and your arm strength. So they're measuring all these different people, their grip strength, their arm strength. They're making a data point for that person. Another person's grip strength and arm strength, they make a data point for that person. And they have all this data displayed on a graph to see if there's an overall trend. Now in a scatter plot, we don't connect these dots. Instead, what we do is we create a line of best fit. And a line of best fit is going to be drawn through the average of these points to kind of show the overall trend that exists between these two variables that are being shown on the graph. A line of best fit could be curved or linear, but in this class for AP Bio, you guys just have to know how to draw a linear line of best fit. And so basically you're going to try to make a straight line go through what you think is the average of all of these points. And so I have a couple examples on this next slide. So you can kind of see here, they drew a line, a single line going through the average of these points. So there's roughly the same amount of dots above and below the line, and it's going through some of the dots. That's a line of best fit. Or even right here in this mess, does seem to be an overall slight trend upward, and that's the line of best fit right there. And then sometimes you might just have a bunch of random dots and you don't see any trend on your scatter plot. And so we'll practice drawing lines of best fit for different scatter plots that we encounter throughout the school year. That's a scatter plot. And then a line graph, sometimes students mix these up, a scatter plot and a line graph. A line graph, this is another common type of graph that students are pretty familiar with. This is also used to show the relationship between two continuous variables. So again, we're looking at two variables that exist along a whole continuous range of values. And we're tracking how those values are changing. Now, typically, most commonly, not always, but most of the time, we usually use a line graph to track how something's changing over time. So when we're looking at how something is changing over time, that means that time is going to be one of the variables we're looking at, and that's usually going to be represented on the x-axis. And the thing that we're measuring and how it's changing over time is going to be on the y-axis. And that's usually the best situation where we're going to use a line graph, because we want to see when these values are going up and when they're going down over time for this variable that we're measuring over time. Now, the only time we would choose a line graph over a scatter plot is because it doesn't always have to be time. So students they have a misconception that you would only use a line graph if it's time. When actually there's some times where you might be looking at different times but not using a line graph, and it gets kind of confusing. And then sometimes there's multiple graphs you could choose from. One might be a little better than the other, but it's all fair game. Sometimes there's two different types of graphs you could make for the same data. But really, a line graph is going to be used over a scatter plot when we actually don't want to see if there's an overall trend, but we actually do care what's happening between point to point to point to point. And we do want to see the changes that go up and the changes that go down. And that's important for the conclusions that we're trying to make from our data. So specifically over time, that's really helpful because we want to know when certain values are going up and when they're going down, or when they're not changing over time. And so that would be different than a scatter plot, because in the scatter plot, we're not seeing when values are going up or back down or decreasing or staying the same. We're just seeing overall big picture if there's a general trend. Whereas in a line graph, usually you're not going to have an overall general trend. You're going to see changes between those variables occurring in different ways. And so that's when we would plot our data and then connect the dots to see that. And then we also can then make inferences about data that we didn't collect. So I didn't take data at, like in this graph down here, that's tracking different times of the day and the number of people at a store. And so I don't know how many people are at the store at 12:30, but I can use my line graph to infer how many people were there at 12:30. And so that's another benefit of using a line graph when it's appropriate, is you can infer things about data points you didn't actually collect data on. And then lastly is a pie chart, and this just shows, this is when we have categorical groups like a bar graph, and we're comparing them proportionally with one another. So usually we're looking at parts of a whole, and so we're looking at how data falls into different categories and how those categories represent different proportions of the overall whole. And so this is usually when we're looking at percentages and when things are going to add up to 100% kind of situation. And so, again, usually students are pretty familiar with pie charts. So different categories that add up to 100%. And you're looking at the proportion of each of them or the percentage of each of them compared to one another. That's a pie chart. Now, the very last slide on here is how to construct a graph, which we're going to do very often in this class, especially in Unit 0. We're actually going to do one example in this video before I sign off. But here are some important components for a graph when you guys are constructing a graph, even especially on an AP test, but including tests in my class or assignments that you do in my class or labs that we're doing. First of all, you should have a descriptive title. And so you can see on this graph, it has a title. It's showing the relation between fertilizer and plant growth. Good enough. It's very descriptive. I know exactly what I'm about to look at. You need to label the axes. So the x-axis and the y-axis should be labeled and include units if applicable. So what they're doing is they're looking at different amounts of fertilizer and how it affects and how much the plant is growing. And so the fertilizer, which is the independent variable, it seems like that they're changing the amount of fertilizer, and then the dependent variable is how much the plant's growing. And usually we do by default put the independent variable on the x-axis and the dependent variable on the y-axis. But anyway, these numbers, these are the different amounts of fertilizer, so they labeled it fertilizer, and there's units. So these represent grams of fertilizer. So this is 2 grams, 3 grams, 4 grams. So you have to include the units. You can't just put fertilizer and then expect someone to figure it out. I don't know if these are pounds of fertilizer or tons of fertilizer, or I have no idea. Different numbered types of fertilizer. So this is talking about grams of fertilizer. And then plant growth, again, they're measuring how much these plants are growing with these different amounts of fertilizer. That's the unit that they're using is centimeters, which is important to know that these aren't feet or meters tall, it's centimeters tall. So they included the units, which you need to do if there's units to include. Which in this case there are for both axes. And then you have to scale the x and the y axis. A scale means you have to figure out what does every box or unit represent on your graph, so that in a way that you can display the data in a way that takes up most of your graph, but also fits on the space that you're provided. So on this graph, you guys can see on the x-axis, every unit, every box represents 0.5 grams. That's their scale, and it's consistent all the way across. Like this is 2.5, then 3, then 3.5, then 4, then 4.5, then 5. And on their y-axis, they have a different scale, which is totally normal and fine. On their y-axis, it goes from 20 to 32 to 44, but every unit on here, it looks like represents 6 centimeters. So this is 20, this is 26, then 32, then 38, then 44, then 50, then 56, and so on. They have a consistent scale set up on their y-axis. So you need all of that set up on your axis. They should be labeled, include units. And then lastly, you need to have, obviously, the data plotted. And in this case, we have 2 continuous variables, and we're trying to see if there's an overall trend. So this is a scatter plot, and then they're drawing a line of best fit through that data. And that's how you construct a graph. So let's do one real quick. In your notes, you guys have, at the very end of topic 2 in your notes, you guys have a question on the left-hand side right here, where it actually wants you to make a graph. For our first graph, we'll do a really easy one, using the goldfish experiment. And the data that we collected from the goldfish experiment in topic 1, the fake experiment that I came up with in topic 1. And so let's take that data and graph it. And so it wants you to fill in this data table first, and then we're going to graph that data. And so pull out your notes so that you can fill this in and get some of your homework assignment done out of the way. But if I go find that slide with the fish in topic 1, which was right here, here's what happened. So you guys can see the temperature was 20 degrees and then it went to 10 degrees. So that's when the temperature dropped 10 degrees. This is when the temperature dropped 5 degrees. This is when the temperature didn't change. It changed 0 degrees. This one changed positive 5 degrees. This one changed positive 10 degrees. And here are their changes in respiration rates. So what I'm going to do is I'm going to pull up some scratch paper. And I'll go ahead and do this with you. I actually already copied down the changes in respiration rates. So for the changes in water temperature, when the water went down 10 degrees Celsius, from 20 to 10 degrees, the respiration rate dropped 15 breaths per minute. And so I went ahead and filled this in, and now I'm going to plot it. And so I have a graph set up. You guys are given a graph that's 10 by 10 boxes in your notes, which means you have to fit your data on that graph in a nice way that is visually pleasing, but also fits on that provided space. You can't add boxes. This is very important on the AP test. On the AP test, when they ask you to make a graph, they're going to give you a template, a certain amount of boxes to use, and you have to fit your data on that. You can't go beyond it. So you have to be very thoughtful with how you're going to lay out that data. So for this, we have 2 different continuous variables actually. So like the change in water temperature, that's like a continuous variable that could be any value along a continuous range. And then their change in respiration rate, which could be a continuous set of numbers along a continuous spectrum of values. And so one of these is going to go on the x-axis and one of them is going to go on the y-axis. Since the change in water temperature was the independent variable, I'm going to put that on the x-axis. And so what I have to do is I have to set up a scale here that's going to fit these numbers. So my highest number is positive 10 and my lowest number is negative 10. And I need to fit all of that on here nicely. So that's that's a range of 20 from negative 10 to positive 10. That's a range of 20. And I have 10 boxes here. So I'm going to say every box equals 2, and that would perfectly fit my data, which would be super convenient. And so I'm going to start at negative 10. And this is also a good example because you guys aren't used to using negative numbers. So I'll put negative 10 there. It's fine. It doesn't have to be 0 right there. I'm going to start with negative 10. And I'm going to say every space on the x-axis is 2. So this is negative 10. This is going to be negative 8, negative 6, negative 4, negative 2. This is going to be 0, positive 2, positive 4, positive 6, positive 8, and then positive 10. Right, and so now I've fit and I've scaled this axis now. You don't have to label every single box unless you really want to, but anyone can look at this and figure out on their own that, okay, every unit equals 2, right? So that's my scale on my x-axis. And then I'm going to label this change in water temperature. And there's units. This is in degrees Celsius that the water temperature is changing. And then let's set up the other axis, the y-axis. On the y-axis, I'm going to look at the change in respiration rate. And now, again, I have to fit all these values on the y-axis. So if you guys look, my lowest value is -15 all the way to +25. And let's say I want to add some buffer space. It doesn't have to perfectly fit on here. Let's say I want to go from like -20 to +30 on here. So it kind of fits all the data with some extra space. -20 to +30 would fit all of this. And that's a range of 50. And so if I have 10 boxes here, I'm going to go ahead and make every box equal 5, I think would work. So if I start, like, let's say I start at -20, because you can start at whatever, you don't have to start at 0. So that's -20. I'm going to say every box, every unit equals 5. So this would be -15. This would be -10. I'll go ahead and label it. This would be -5. This would be 0, +5, +10, 15, 20, 25, 30. There we go. I've set up my scale. Every unit equals 5. And then I labeled some of them, but anyone could figure that out by looking at it. And then I'm going to label the axes. I'm going to say change in respiration rate. I'm just going to put RR. And that's measured, the unit for that is breaths per minute. There we go. I have successfully set up my 2x and y, my 2 axes, my x and my y axis. So now I'm going to plot the data, the fun part. And so at -10, and when the water temperature changed to -10, the change in respiration rate was -15. So I'm going to put a dot right here. A dot. And you can see I'm constructing what looks like it's becoming a bunch of dots I'm going to put on here because I have 2 continuous variables. So it's not a bar graph because these aren't specific categories. And then at that point, I'm going to have to decide, is this a scatter plot or a line graph? But we'll get to that in a second. So I'm going to go ahead and finish plotting these. So 5 would be between, so this is -6 and -4. So 5 would be right here in the middle, right? -5. And it changed -10, so right there. So be careful when you're graphing. And then 0, 0, that one's easy. And then +5, which again is right here. And that went to up 15. And then +10, it changed 25. So then we end right here. Okay, so there's my data points plotted. Now really, for this one, this actually is a good example of data that really you could do a scatter plot or call this a line graph. Either or would be acceptable in my opinion. Now, since we are looking at what looks like an overall trend, it kind of makes sense that we should probably call this a scatter plot and then draw a line of best fit through our data. Just because there does seem to be an overall trend. As one variable is increasing, the other variable also is increasing. We can see in our data. It is a little weird because usually you'd have a lot more data points from a lot more fish that we would have changed the temperature of and see how the respiration rate was affected. But either way, you could just make a line of best fit, or you could make this a line graph and connect the dots because maybe you are interested at different temperatures. There are different things happening maybe. I mean, it doesn't look like it too much, but especially if like at certain temperatures it was going up for the respiration rate and then there was a decline later on, then yeah, for sure a line graph would be better because there isn't an overall change, and depending on where the temperature's at, different things are happening. But let's go ahead and pretend this is a scatter plot. And so I'm going to make a line of best fit. You guys can see that these dots do not all perfectly connect in a straight line. So you're going to pull out a straight edge like your ID card or a ruler, and you're going to try to make a line through the average of these points. And so it can go through some of the points, but you kind of want an equal number of dots above and below the line. Since you're doing this by hand, which on the AP test you would also have to do this by hand if you have to make a line of best fit, it's obviously there's going to be room for error. We could use a computer software and it would plot the perfect line of best fit, but we're not going to do that. We're always going to do it by hand. And so I'm going to go ahead and make mine like, let's see, let's do, I don't know. Let me go ahead and do this. good enough, right? So I have some dots above it, some below it. Looks like the average to me. And that would be my scatter plot. And then you would want a descriptive title here. I'm going to put, I'll say, well, I could just make it as simple as saying the effect of changes in water temperature on fish's respiration rate, you know, like, which again, a lot of times the titles, they should be long and descriptive. So let's just write that. I'll go ahead and say, actually, I'll do this. Fish respiration rate response, I'm abbreviating here, to changes in water temperature. There's my title, and that's it. Anyway, that was topic 2. There's a couple more questions you guys need to answer on the left side, not a lot though. And I know this video was longer, but hopefully that example was helpful. But that's it. I'll see you guys soon.